All right, so continuing on here, we were discussing continuity, and the next item that we wanted to talk about is, so let's assume that we know that a function is continuous at a point c, at a point x equals c. And let's assume actually that we know two functions are continuous at that same point. What can we say? Can we start to combine the functions? How can we, what else can we say given that information? And so here's a handy theorem. So if b is a real number and f and g are both continuous at x equals c, okay? So you got two functions, f and g, they're both continuous at this point, x equals c, and b is just a constant. Then the following is true. Okay, so first of all, the constant times f is continuous. At x equals c. Okay, so that's natural. Secondarily, the two functions f and g, you can add or subtract them, and you retain the continuity. The sum is continuous, or the difference. Thirdly, you can multiply them. Okay, so the product of f and g is continuous at x equals c, and the ratio of the two functions is also continuous. Okay, so that is an interesting and helpful feature, right? So we'll get into some examples in a second of, a bunch of these, start looking at combinations of more complicated functions and seeing what we can see. Before we do that, let's build up a little bit of a stockpile of types of functions that are everywhere continuous. So the following functions are everywhere continuous. Yeah, so remember, everywhere continuous means that they're continuous on the entire real number line. So here we'll limit this a little bit. We'll say the following functions are continuous at every point in their domains. So the following functions are everywhere continuous on their domains. Okay, so some of these will have a restricted domain. So first up would be the polynomials. Okay, so remember what those are. Those are functions that look like p of x equals what, like a to the n x to the n plus a to the n minus 1 x to the n minus 1 plus dot 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 plus a1 x plus a0, right? Where the a terms here are constants, they're real numbers, and the n's, the exponents here, are all positive integers. Right, so these are the normal polynomials. So those are everywhere continuous. And now actually it turns out that polynomials are continuous on the entire real number line. So there's no real number that you can't plug into a polynomial. And their limits are always nice and clean due to the continuity, right? Due to the fact that they're everywhere continuous. Rational functions are also everywhere continuous on their domains. Right? So if you've got like r of x equals p of x over q of x, where q of x is non-zero, of course. Okay, so those functions are also everywhere continuous on their domains. Okay, and let's see, radical functions, another example. of everywhere continuous functions. All right, so that'd be something like f of x equals the nth root of x. The trig functions. Things like sine of x, cosine of x, etc. And then the exponential and logarithmic functions as well. Those are also everywhere continuous on their domains. So things like f of x equal to a to the x, f of x equal to e to the x, and things like this, natural log of x, right? Those guys. Those are the exponential and logarithmic functions, and those guys are all everywhere continuous on their domains. Okay. Good. So that's an example. That helps us build up a stockpile of kind of knowledge regarding like which functions do we have to worry about, which ones don't we have to worry about. These are the ones we don't have to worry about. So let's see an example of a more exotic function. So something like this. What can we say about that? Is a function like this everywhere continuous? Well, you can kind of think of this as, you can kind of think of g of x equals x and h of x equals e to the x. Right, now this guy, everywhere continuous, right? And this guy as well. Nothing to worry about with e to the x. You can plug in anything you want there, no worries, the limits all work. So f of x is just g of x plus h of x, right, which is x plus e to the x. Now that this right here, given these two being continuous, the sum is continuous, right? That's the previous theorem that we just saw. So nothing to worry about there. So that's good. What about another example? Let's look at, what about f of x equals x squared plus 1 over the cos of x. Is this function everywhere continuous? Yeah, again, let's let g of x equal that numerator. And let's let h of x equal the denominator. Now, we don't have a problem. Like this is a polynomial, this is a trig function, they're both everywhere continuous on the whole real number line. So no problem, right? Well, yeah, I mean, what we could say is f is continuous. Well, we could say it's everywhere continuous on its domain. All right, but we have to be a little bit careful, right? Because we do get the everywhere continuous feature from this. So that guarantees that f of x is everywhere continuous on its domain, but we do have to consider its domain, right? Because the cosine of x can equal 0, right? So the domain of f is limited. So it's no longer the whole real number line. Right, so a little bit of a consideration, right? So the cosine, right, is is going to be 0 at values like pi over 2 and at 3 pi over 2, and it's going to be 0 at basically as you continue to go around the circle, you've got one here, you've got another one here, you get another one here, you got another one here, right? So every time cosine is equal to 0, then the domain of f is that value is of x is not in the domain of f. But the left-hand limits and the right-hand limits are going to work there still, right? So you still have continuity on the domain, right? So you may look at this and say this is not everywhere continuous on the real number line, and that's very true, because the function is not defined for every real number, right? Because you have cosine of x in the denominator. But the theorem that we just talked through says that that the ratio here of g of x over h of x should be everywhere continuous on its domain, and that's true in this case as well. Okay, so that's kind of an interesting one to think through. All right, let's take a look at another theorem here. These are all useful theorems surrounding continuity. If g is continuous at x equals c, okay, and f is continuous at g of c, okay, then what are we going to do? Well, we're going to compose some functions. Then f composed of g of x, right? Sometimes people prefer to write it like this, is continuous at c as well. Okay, so if you have a function g that's continuous at x of c, and if f is continuous at whatever g of c happens to be, right, then the composition of the two functions is naturally going to be continuous at c as well. Okay, so notice, I mean, this is hopefully like kind of obvious, right? But if g is continuous at x of c, then that means the limit of g at x equals c as x approaches c is g of c, right? And so naturally then that same point would be where f would be evaluated, would be at g of c, right? So g is continuous at x equals c and f is continuous at g of c, then the composition is continuous there as well. Here's an example going through that. So consider, let's say h of x equals sine of 3x. Okay. Now notice that if we say f of x equals sine of x and g of x equals 3x, okay, so notice then that obviously if we define it like this, then f of g of x equals sine of 3x, right? So that's your h of x. Note that f and g, right, so individually these two are everywhere continuous, right? One's a polynomial, the other's a trig function. We saw that these are everywhere continuous. So these are everywhere continuous, right? Basically continuous at all real numbers. And so clearly sine of x would be continuous at whatever 3 times c is, right? Or g of c, 3 times c. And so that implies the composition of these two is everywhere continuous. Okay. Perfect. Okay. Very good. Very good. Let's see here. Let's do this example. I like this one. This is a kind of a different sort of thing. So describe the intervals upon which f of x is continuous. So let's let f of x equal sine of 1 over x or 0. And this is going to be where x is not equal to 0, and this is where x is equal to 0. Okay, so we talked about this one previously. We've seen the sine of 1 over x. This is one that where we don't have an overall limit, right? So the question here is like, what can we say about the intervals upon which this function is continuous? So notice, right? Notice here that g of x equals 1. Let's just set that equal to the inside function, right? 1 over x. This is continuous at all x except for x equals 0. Right? So naturally you can plug in any x here and you get no problems, and the limit would be equal to all of the evaluated values as well, except at x equals 0, right? Because you've got this asymptotic behavior. Now, notice further that right. Notice also that the outside function h of x equals sine of x. Now this guy is continuous everywhere, right? At all real numbers. Right. Okay. So what we could say then is that basically this function here should be continuous at all real numbers except for 0, right? So h of g of x equal to sine of 1 over x is continuous at all real numbers except x equals 0. Right? So you basically would have a problem here, right? So this guy here is not continuous at 0. There's no way to get around that. If you remember what this one looked like, it went like this, right? Right, so no redefinition. This is an example where the inside function has a non-removable discontinuity. So, but everywhere else it's fine. The numbers get very large, they get very small, but that's okay. And we can plug very large numbers and very small numbers into the sine function. That's okay as well. And so basically this guy's good everywhere except for 0. And so what we would say is that the function is continuous if you take like negative infinity up to 0 and 0 up to positive infinity. Right, now obviously very important that these be open. These are open intervals. Naturally they're open, right? At least semi-open. Infinity is not a real number, so you can never have a closed bracket around infinity. But then the 0 is excluded. It's the one point that we can't, where we don't have continuity. Excellent. All right. So, very good. The next, this is a nice little theorem that I think is very intuitive, but I think people tend to kind of like it because they can get it. It's also extremely useful, right? So if f is continuous, on the closed interval AB, all right, and k is any number, between FA and FB. Okay, then there's at least one number C in the interval AB, closed interval AB, such that f of c is equal to k. Okay, so if f is continuous on the closed interval AB and k is any number between f of a and f of b, then there's at least one number between a and b, namely c, such that f of c is equal to k. Now, this is actually really obvious if you draw a picture. So let me draw a picture here. So let's say our function kind of looks like this. It comes down like this, right? And let's say here's A, here's B, right? We're talking a closed interval, so we're including those points. So that would be f of A, and this would be B, f of B. All this theorem is saying is that somewhere, wait, hang on one second. All this theorem is saying is that, let's say k is here. Okay, so k is a number between f of a and f of b. Then there's going to exist some c in here such that f of c is equal to k. Okay, now it's important, right, that this is a good theorem to look at kind of and to really examine the assumption. So we're assuming that f is continuous on a closed interval. Okay, so those two pieces are very important. So let's see an example where we relax the continuity, for example. All right, let's say we've got our a and we've got our b, right? And then this case, let's say that our function kind of comes down, goes like this, and we've got a little bit of a jump here. Okay, so again, here's your f of a, here's your f of b. Okay, now again, if I can find k, there's a k in here, right, for example, and this k, the function has there is no value c between a and b such that f of c is equal to k, right? The function kind of starts above k, and then this gap, it gaps down to below k. So here you can say there does not exist, a c in the interval ab such that f of c is equal to k, right? Namely because of the gap. All right, so this is a nice theorem that you can use for a lot of different things. Here's an example of how we might be able to use this. We want to show that the polynomial f of x equals x cubed plus 2x minus 1 has a 0 on the interval 0 to 1. Okay. Now, first thing to notice is f is everywhere continuous. How do we know that? Well, because it's a polynomial, right? So f is a polynomial, so f is everywhere continuous. That means we don't have to worry about the continuity. I mean, we know that it's continuous on the whole real number line, so clearly it is continuous on this closed interval. Notice here that f of 0, if I plug in this endpoint, I get 0 plus 0 minus 1. And f of 1 is equal to what's that? 1 plus 2 minus 1, right? So there you would get, so it's 1 plus 2, so it'd be 2. All right. Now clearly, f of 0 is less than 0, right? And f of 1 is greater than 0, right? So this is the condition, right, of the previous theorem, right? There we said, all right, I've got an f of a and I've got an f of b. If the function's continuous, then every k in between there must have a c in the range such that f of c is equal to k. Well, so here's what I'm seeing here. I've got a range of 0 to 1, and I can see that range crosses 0. So f of 0 is negative 1, f of 1 is 2. So somewhere between negative 1 and 2, there's obviously the number 0, right? And so that implies there exists a c in 0 to 1 such that f of c is equal to 0, and that's what we mean by a 0, of a polynomial, right? There's going to be some number which satisfies the equation f of x equals 0. And so this is a way to kind of identify quickly whether or not you have a 0 of a polynomial in a range, right? Especially if you know the value of the polynomial for, if you know that, if you can see where, the range is that the polynomial crosses 0, right? You can quickly narrow it down, and you can just be guaranteed of a 0. All right. Okay, so that is a nice example of kind of using continuity. There's all kinds of uses for continuity. It turns out one of the defining characteristics of the real number line is continuity, and it's one of the more interesting things about the real numbers. It separates it, for example, from numbers, sets like the integers and the natural numbers and other number sets. So it's super interesting. We're obviously just barely touching down on continuity in this class, but again, the idea is to just have a working idea of continuity. Now, what we're going to do is we're going to then move into derivatives and later integration, and a condition for the existence of derivatives and integrals is continuity for within the domain, right? So continuities are going to be a building block for some of these higher order calculus features. So, all right, so we'll end it here. The next lecture we'll get into infinite limits. We'll see you then.